Hello, in this video I will finish talking about production and costs. Again, I'm following chapter 5, and today I'm going to focus on the last question: what happens to a firm's costs in the long run? And so, just a quick reminder, in the short run, um, as I said in the previous two videos, a firm's level of capital is fixed, and so the decision that the firm has to make is how much to produce and how much labor to hire to produce the output that the firm is willing to produce. In the long run, capital is not fixed any longer, so the firm not only has to decide how much to produce, but also what combination of capital and labor to use to employ that output. So let's return to the example that I've been using throughout this textbook chapter. I'm going to look at the Cobb-Douglas production function where the output is 10 times square root capital square root labor. And the question that I want to ask is, suppose we want to produce 240 units of output. What combinations of capital and labor will do that? And I can give you examples of answers. For example, if you take 144 units of labor and 4 units of capital, you'll get 240 units of output, or take 36 labor, 16 capital, or take 9 labor, 64 capital. All these combinations will result in exactly 240 units of output given this production function. The principle that is at work here is that to maximize profits, the company has to be minimizing costs. If for any reason it had decided to produce 240 units, it should do so in the cheapest way possible. So we need to look at all possible combinations of capital and labor that result in 240 units of output, and among these combinations we need to find the cheapest one. So let's see how we're gonna frame that problem. First of all, we're gonna look at an isoquant. So here's a new concept. We're gonna look at the curve that contains all combinations of labor and capital that produce exactly the desired amount of output. And so in our example, the isoquant is gonna look like that. The isoquant for 240 is gonna be familiar U-shaped convex function with high amounts of capital when labor is low, high amounts of labor when capital is low, and relatively small amounts of capital and labor when they're far from the origins. So that's an isoquant. Second concept that we need to introduce is the concept of isocost, a curve that contains all combinations of labor and capital that costs exactly the same. So independent of how much labor and capital produces, say we have $15,000 to spend on labor and capital. Let's plot all the points that cost exactly $15,000. And if we do that, we'll get an equation that equates our cost, our expenditure, times how much it will cost to buy labor at the wage rate of 125 plus how much it will cost to rent capital at the rental price of 200. And so if we do that, the isocost will be straight lines in this labor capital coordinates. So for example, the red line here corresponds to the cost of $15,000. So all labor capital combinations that cost $15,000 are on the red line. The yellow line corresponds to a cost of $10,000, and the green line corresponds to a cost of $5,000. And we want to produce 240. That means we want to find a point on the blue curve that costs the cheapest. So formally, the problem can be written down as follows. We want to minimize the cost of production so that, subject to the output constraint, the required amount of output is produced. So this is the description of the problem in general terms. With respect to our example, it can be written down as minimize the expression 125L plus 200K, that is the cost of hiring L units of labor and K units of capital, subject to 240 units being produced using our production function. And based on this graph, you can see that it will cost at least $5,000 because it's infeasible to produce 240 units at $5,000, and it's probably going to cost less than $10,000 because, well, we can go below the yellow curve and still produce 240. So we can possibly find a cheaper way to do so. But before I solve this problem with you, let me show you a trick and see how quickly you notice what I'm doing. Let's see here. So the trick is going to be as follows. I'm going to press the button, and the only thing that I did here is I replaced the graph on the screen. And on that graph, the lines are the same, but now the bottom label is good X, the vertical axis is labeled good Y, and instead of an isoquant, I'm using a utility curve, and I'm labeling that utility 240. And instead of a isocost, the cost line, I'm using a budget line. And that picture should be familiar to you now, because here we're looking at an indifference curve and 3 budget lines. So we're looking at the world of utility maximization for a consumer. And so because I was able to jump from the firm's problem to the consumer's problem by simply relabeling the curves, probably I could be able to say something about the solution to the firm's problem, knowing the solution to the consumer's problem. So let's compare the two. First of all, notice that the isoquant behaves like an indifference curve. It is convex, that means its slope is increasing in absolute terms, and it's sort of U-shaped when you look at it. And then isocost behaves like a budget constraint. So that means it looks like a straight line in the labor capital coordinates. Now, let's keep the picture in mind. It doesn't matter what exactly is on the axis. And let's just write the two problems back to back. So we have the cost minimization problem. Minimize cost subject to the production constraint. The consumer in the utility maximization problem that we looked at before solves a slightly different problem. For the consumer, the goal is to maximize utility, and we can think of a Cobb-Douglas utility just like we can think of a Cobb-Douglas production function, because we can just replace capital and labor with good X and good Y, so that would be a legit utility function. And so we want to maximize utility subject to the budget constraint that we only have an income of $M that we need to spend between good X and good Y. So in one case, we're maximizing the utility subject to a budget constraint. So we fix a budget line and we want to find the curve that is farthest away from the origin that is still feasible given the budget line. And in the cost minimization case, we fix a curve and we want to find a line, a cost line that is closest to the origin. So in a sense, the consumer and the firm are solving the reverse problems. One has a fixed budget and wants to go as far as possible in terms of utility. The other one has a fixed output and wants to go as close as possible to the origin in terms of the cost. What does it entail? We know that for the consumer, in the optimal consumption bundle, the slope of the indifference curve has to be equal to the slope of the budget line. They have to be tangent to each other. So to maximize utility, find an indifference curve that's tangent to the budget line. Well, it turns out that for the cost minimization problem, the optimal condition is exactly the same. The slope of the isoquant, the slope of the blue line, has to be the same as the slope of the isocost, the yellow or the red line. Again, to minimize the cost, if you want to find the line that is closest to the origin, well, keep moving it down until you're only slightly touching the isoquant. So the same principle. At the optimal point, the two curves have to be tangent to each other, so that their slopes have to be the same. And we also have a condition for tangency in the utility maximization world, and that condition is the slope of the indifference curve, that is the marginal utility of x divided by marginal utility of y, has to equal the price ratio. And the same condition written down in the cost minimization world simply says that the marginal product of labor divided by marginal product of capital has to equal the price ratio. Because the isoquant is derived from a production function, we can talk about product rather than utility. And the price ratio is just the price per unit of capital and labor that you can hire. And recall, because it's good x on the horizontal and good y on the vertical axis, we have x over y, x over y. And in the other world, we have labor and capital, so it's going to be labor over capital, price of labor over price of capital. So exactly the same. Now, back to the firm problem. Here is the problem written down in general terms, and the conditions that will tell us what the solution is, again, in general terms. But let's work it out through an example. Have minimize 125 times labor plus 200 times capital, subject to output has to equal to 240. We don't know yet what marginal product of labor and capital are, but we can define them now the following way. We have a production function C times capital raised to the power A times labor raised to the power B. And marginal product of labor is just an expression that tells you how much the output changes if you vary labor slightly. So in math terms, marginal product of labor is a partial derivative of the production function with respect to labor. To find the partial derivative, you just need to treat everything that doesn't have to do with labor as a constant and labor as the only variable of interest. So treat this function as a function of labor and find the derivative with respect to it. And the convenient way to write it down is that it's just the production function itself, Q itself, times the exponent coefficient B divided by labor. Because when you take the derivative, you get B times L to the power B minus 1, or alternatively B times L to the B divided by L. So we're just taking the production function, multiplying it by coefficient B, and dividing it by labor. For marginal product of capital, we're doing the same, taking the same production function, looking at the derivative with respect to capital, thinking of labor as a constant, so we multiply by coefficient of capital and divide by capital. And so then our condition can be simplified to the ratio of the two, since Q's cancel each other out, is equal to B times K divided by A times L. And we can take this ratio, plug it into the optimal condition, so we'll get B times K divided by A times L equals the price ratio for the inputs. And then let's take the next step. B and A are 1/2 in our story, so we can get rid of those. And W and R are 125 and 200. So K over L has to be 125 over 200. So this optimal condition gives us the basically the golden proportion in which capital and labor should be employed in the long run when both are available at any rate. With that in mind, we can express capital in terms of labor. We can say that capital is 0.6 of labor, because if we simplify this proportion by bringing labor to the right-hand side, and 125 divided by 200 is exactly 0.6. So we need to hire certain number of labor units, and the corresponding capital has to be 0.6 times labor. And then we can go back to the constraint. We know which proportion capital and labor have to be hired in, and we just need to find out how much labor exactly we need to hire. So take this equation, 240 equals 10 square root K square root L. replace k with 0.6L, and you'll get 240 equals 10.6L to the 1/2, that is square root times square root L. And now it's just an equation in one variable. Solve it for labor, and you'll get that labor is approximately 31, and then capital is approximately 18.6, and the minimum cost is 7,600. Again, approximately. I'm rounding for convenience, but you can see that the cost does fall in between 5 and 10,000, just like we said before. So that's the idea. You're minimizing the function with respect to a constraint. Using the optimal condition, you find the optimal proportion of capital to labor, and then knowing that optimal proportion, you can actually figure out how much labor and how much capital you actually need to employ, and that's what the cost is going to be. And this is the kind of problem that the firm is solving in the long run. Now, the next thing that I'd like to do is I'd like to talk about the relationship between the short-run costs of a company and the long-run costs of a company. And here I'm going to use an example that I used in the previous videos too. In the short run, suppose that the level of capital is fixed at 25. It gives us a total cost of q squared over 20 plus 5,000. If you don't remember how I got it, go back to the 2 previous videos and see how I did it. And so the average cost, that is total cost divided by the output, is going to be q over 20 plus 5,000 q. Let's now do a similar type of derivation. And if you're curious, you can double check my calculations on your own. But suppose that instead of a short run capital level of 25, I'm going to look at a short run capital level of 50. That will give me a slightly different total cost, q squared over 40 plus 10,000. You can see that because I doubled the amount of capital, my fixed cost component doubled, my variable cost component actually halved, and the average costs reflect that as well. Let's double the capital one more time. For the capital of 100, total costs are q squared over 80 plus 20,000. Average costs are q over 80 plus 20,000 divided by q. So basically, in the short run, for every level of capital, I will get a distinct total cost and distinct average cost. Finally, let's write down what happens in the long run when the amount of capital is variable. So that means for every level of output that I want to produce, I will be doing it the cheapest way possible. This gives me a rather simple expression of total cost of 32q. Well, it's not exactly 32, it's approximately 32. And the average cost is then approximately 32. So let's graph all this 1, 2, 3, 4 costs together on the same graph. What do we see? Well, the blue line is the first short-run average cost, and you can see that it's U-shaped. The red line is the second, and yellow is the third short-run average cost. And all of them are U-shaped on this graph. In the side point, I'm using a slightly disproportionate scale to actually ensure that the curves look like they're U-shaped, even if their curvature is not very pronounced, so to speak. What is the relationship between three different short-run average costs? You can see that as we increase the amount of capital, our fixed costs increase, and so our average costs rise for small output levels. We see that we start with a fixed cost of 5,000, and then it's 10, and then it's 20,000. So clearly, producing very little is more expensive when you have more capital. On the other hand, as we increase capital, our variable cost component falls from q squared over 20 to q squared over 40 to q squared over 80. And so producing a lot makes sense with more capital. And so when the amount of capital is large, the yellow cost curve will ultimately be the lowest cost curve, higher than red, lower than red, and lower than blue, although you don't see it in the graph here. So when we increase the amount of capital, it's like we're taking this U-shaped curve and we shift it to the right. So the red line can be thought of the blue line shifted to the right slightly, and the yellow line is even farther shift to the right. So it's just a bunch of U-shaped curves shifted to the right as the capital increases. What about the long run cost curve? Well, in the long run, we're saying if we were to produce a particular level of output, what is the cheapest way of doing so? What is the cheapest amount of capital and labor we need to produce a particular value of Q? Well, then by definition, the long run costs will be the lowest cost possible of all possible short run combinations. So think about all possible levels of capital, not just these three, but all of them, from 0 to infinity. In the long run, to produce 240 units, we'll pick a combination that will give us the lowest cost. In fact, if you remember the answer, that combination corresponds to capital equal to 18.6, so slightly under 25. So that will be, there's going to be a short run average cost curve that was going to correspond to the long run solution for 240. For a different level of output, we will pick a different level of capital. So for each level of output, we'll pick a particular level of capital that corresponds to the lowest short run average cost ever. And so this simply means that the long run average cost curve is what's called the lower envelope. If you drew all possible short run average cost curve on the graph and then simply highlighted the minimum for every quantity, you'll get the long run cost curve. And in this particular example, that minimum is 32, no matter what's going on. In other cases, that minimum could be increasing or decreasing. So because we have constant long run average cost curve, we can talk about constant returns to scale. If we were to scale up our production for this company, no matter how much it is going to produce, the cheapest way to do so would be to produce at exactly $32 per unit. You want 400, minimum cost $32 per unit. You want 400,000, average cost is going to be $32 per unit. Constant returns. No reduction in costs or no increases in costs as you scale things up. Okay, this is pretty much everything that I wanted to talk about with respect to the firm's costs in the long run. In the next video, I'm going to talk about the firm's decisions in the long run, and thus we can wrap up the story of the competitive industry in the long run. Thank you.